So greetings to all my viewers. Today we are going to discuss unit number 3, that will be elements of hydropower plants. In my previous two lectures I have covered all the basic principle of construction and working of a hydroelectric power plant, the basic components of hydroelectric power plant and the basic constituents what are involved in hydropower generation. In this module, in this unit, we are going to see the key elements of hydropower plant. So, we will start with the first heading called as components of a hydroelectric scheme. Most of the hydro schemes in hilly areas in India are high head and medium head and have the same basic and common components of hydroelectric head. The major components of a hydroelectric schemes can be listed as, I have divided the major schemes into some 6-7 categories that we will go through one by one. First one is diversion and intake structure, next is water conductor system, next is desilting chamber, then we have forebay balancing reservoir and spilling arrangement, then we have penstock, then we have surge tank, then we have powerhouse equipment and system, and at last we have tail race channel. So, in brief we will go through one by one each. First one is our intake structure. An intake structure is an arrangement by which water is diverted for the required use. It means wherever you require the water, it will be given there. The intake is an arrangement which allows water to be taken from its source and then discharged into the conveyance system from where it is led to the desired use, like hydroelectric power generation. Arrangements for routing high flood discharge are also made. Based upon operating heads, intakes may be classified as low head, medium head and high head. All about discussions about head we have already done in our previous lectures. In this module also we will talk something about heads. Now, second one is water conductor system. In that we have feeder channel and we have head race channel. In feeder channel, this is provided from intake to desilting tank and carry sediment ridden water. The velocity in the section should be enough so that the sediments present in the water may not get deposited at the channel bed. Now, next one is our head race channel. This is provided from desilting tank to forebay tank. It carries silt free water because you have to ensure that there is either no silt or least possible silt in the flowing water. Then the channel may be of following types: open channel made up of RCC, cut and cover, and steel pipes are provided in reaches where the slopes are more, or you can say the slopes are geologically unstable. Then the structure can also be of RCC, cut and cover, then concrete hume pipe. Then the structure can also be made up of PVC, HDPE, fiberglass, steel pipe. So, these are some material which are used to manufacture the flow channel. In open channel, it could be trapezoidal with thin concrete lining or rectangular with masonry or concrete wall. For excess, provision needs to be made only for a bridle path to economize the cost, as also avoid the unnecessary hill slope cutting. Loss of water due to seepage, data on some may be obtained or representative scheme so that its significance can be assessed. Now, the third component is desilting and sediment controlling actions. Sediment control by excluders or ejectors is accompanied by using following devices. Settling basin is one of the most effective devices for removing sediments particles from the flowing water. The reduction in the velocity of flow in the settling basin is caused by expansion of the channel over the cross section over the entire length of the basin. Such reduction in velocity also reduces the bed shear stress and the turbulence. Now, reduction in the velocity, shear stress and the turbulence, if adequate, stops the bed material from moving and also causes part of the suspended material to be get deposited. Once the minimum size of sediment to be removed has been decided, the design of the settling basin involves the determination of the depth and length of the basin and choice of the method removal of the deposited material. Now, the next component in this scheme is forebay tank, that is also known as balancing reservoir and spilling arrangements. The purpose of forebay tank or balancing reservoir can be listed as, there are multiple, so I have just listed out in point wise. Balancing storage provide storage of 1 to 4 hours during peak hours to supply the same during peak hours and thus meet variable demand, justifying economics. Then 4-bay tank provides immediate water demand for starting the units. It has 2-3 minutes capacity, you can say, and enough submergence of penstock intake to prevent vortex formation and air entry. Then it is suitable sideways spillway to provide safety to the system equal to the design discharge. The next component, the very key component in this scheme is penstock. We have also discussed in my last lecture about penstock. Various types of material nowadays available for manufacturing the pipes, which could be used as penstocks for hydropower development in the country. The merits and demerits of these pipes vary widely. So, depending upon application also, we go through the choice of this penstock. For making selection of the type of pipe that should be used for a specific site, several factors such as basic cost, transportation and erection and availability of material and skill should be considered thoroughly, and a comparative analysis shall lead to the designer to make some decision about the choice of penstock. Then in my few discussions I am going to give you some standards, some layouts of design of penstock, some criterion we adopt. So, number 1, you can say criterion for hydraulic design of penstock, IS 11625 1986. Then we follow criterion for structural design of penstock, IS 11639 part 1 of 1986. The most common types of pipes which could be used as a penstock are, which we normally used in this hydropower plant, is first one we have steel pipe, next sometimes we are going for this PVC material, and mostly we go for reinforced concrete pipe and pre-stressed concrete pipe. Now, next component in this scheme is surge tank. Surge tanks are required to be provided on turbine penstock installation for speed regulation on many bases. Few basic I will discuss it here also. Surge tanks are provided where the resulting reduction in water hammer pressure will provide a more economical turbine penstock installation. A surge tank also be provided for the condition where computed percent of speed rise based on rejection of the entire rated load for a unit operating independently cannot be reduced to about 35% by other practical methods. This is required for hydro unit meant for isolated operation. The speed rise parameter may increase to about 45% for unit designed for system frequency regulation. Now, next component we have is tail race channel. Each unit has its own tail race. Rectangular section, it is a rectangular section with bed scope as per terrain is provided for the tail race channel. And finally, we have power house. Its layout we will first discuss. The two common types of hydropower plants in India are, we have already discussed, low head power plants and then medium head and high head also. High or medium we sometime combine as the same category. Low head plants built into irrigation system of canals and dams in the plant, and then comparatively high or medium head power plants in the mountain valleys on streams, rivers, tributaries constitutes a small hydropower station. Now, we will go for some separate discussions under the heading called as power plant auxiliary equipments and appurtenant facilities. Space to be provided in a powerhouse for the following auxiliary equipment and appurtenant facilities. Number 1, we have turbine governor and shut off valve, then we have generator, then we have unit and auxiliary power transformers, then we have control cubicle and relaying equipment, then we have neutral grounding cubicle and surge protection, then we have station battery, then we have cooling water system, then we have drainage and dewatering system, we have ventilation system, we have fire extinguishers, we have compressed air system, and finally we have powerhouse cranes or crane. Now, my discussion will directly come to the hydraulic turbines, which are the backbone of any hydroelectric power plant. Hydraulic turbines and governors. First, I will start my discussion with classification and types of turbine. The hydraulic turbine is a mechanical device that converts the potential energy contained in an elevated body of the water by the means of its head into rotational mechanical energy. Impulse or velocity wheel known as water mill is of great antiquity. Thousands of these are existing in the Himalayan region to be used for grinding grain. An improved variety of up to about 5 kilowatt capacity is also used to generate electricity by belt coupling to increase the speed and use as standard generator. Now, the modern turbines are very efficient, long lasting and can be started quickly and can go from no speed load to full speed load in just about 4 to 10 seconds and then can drop load instantly without damage. Now, I am going to classify the turbine as per the operating capacity. It can be classified as micro, mini and small, and then large. Micro is having capacity up to 100 kilowatt, mini 101 to 2000 kilowatt, then we have small 2001 to 2005 sorry 25,000 kilowatt, and then large above 25,000 kilowatt. So, these are the classifications of turbine. Now, further based upon action, turbine can be either reaction or impulse. In the previous lecture I have also discussed. The turbine types indicates the manner in which the water causes the turbine runner to rotate. Reaction turbine operates with their runners fully flooded and develops torque because of the reaction of water pressure against the runner blades. Now, talking about the impulse turbine operates with their runner in air and converts the water pressure energy into kinetic energy of the jet that impinges onto the runner. Impinges means strikes, impinges onto the runner buckets to develop the required torque. Reaction turbine can also be classified as Francis turbine, that is also sometimes referred as mixed flow or axial flow turbine. Axial flow turbines are available with both fixed blade that we call as propeller, and then with variable pitch blades that we call it as Kaplan. Both axial flow, propeller and Kaplan, and then Francis turbine may be mounted either horizontally or vertically. Additionally, propeller turbine may be slant mounted. It means its axis can be inclined to some angle from the vertical. Now, Pelton wheel, it is an impulse turbine which is having one or more free jets discharging into an aerated space and impinging on the buckets of a runner. It is having the maximum efficiencies. The efficiencies are often 90% and above. In general, an impulse turbine will not be competitive in the cost with a reaction turbine in overlapping range. However, certain hydraulic condition search protection requirements may warrant investigation into the suitability of an impulse turbine in the overlapping head. Single nozzle impulse turbine has a very flat efficiency curve and may be operated down to loads of 25% of rated capacity, operating at a good efficiency. For multi-nozzle units, the range is even broader because the number of operating jets can be varied. Control of this type of turbine is maintained by hydraulically operated needle nozzles in each jet. In addition, a jet deflector is provided for emergency shutdown. The deflector diverts the water jet from the buckets to the wall on the pit liner. This features provides surge protection for the penstock without the need for a pressure valve because load can be rapidly removed from the generator without changing the flow rate. Now, let us have some small discussions about Francis turbine. A Francis turbine is one having a runner with fixed buckets that are also referred to as vanes, usually 9 or more, to which the water enters the turbine in a radial direction with respect to the shaft and is discharged in axial direction. Principal component consists of a runner, a water supply case to convey the water to the runner, wicket gates to control the quantity of water and distribute it equally to the runner, and a draft tube to convey the water away from the turbines. It exists in large number throughout the world. Francis turbine has application at many places. It is applied at head ranges generally from about 15 to 750 meters and in power ranges from about 0.25 to 800 megawatt per unit. Here are also numerous small units at very low head, for example 1.5 meters and output for example 2 kilowatt, but these are not typical of the current practice. Then now let us have some discussions on axial flow turbines. Axial flow turbines are those in which, though the runner is aligned with the axis of the rotation, the axial flow hydraulic turbines have been used for net heads up to 75 meter with power output up to 200 megawatt. However, they are generally used in head applications below 35 meters. S type turbines are also used for below 30 meter heads and 8 megawatt power capacity. Bulb and pit units can be used to about 25 meters head and 100 megawatt capacity. By these data, I am just trying to give, depending upon capacity, depending upon head, which type of turbine can be employed. Specific mechanical designs, civil construction and economic factors must be given full considerations when selecting among these three axial flow turbine arrangements. A propeller turbine is one having a runner with 4, 5 or 6 blades in which the water passes through the runner in axial direction with respect to the shaft. The pitch of the blades may be fixed or movable. Principal component consist of a water supply case, wicket gates, a runner and a draft tube. So, these are the basic components. The efficiency curve of a typical fixed blade propeller turbine forms a sharp peak more abrupt than Francis turbine. For variable pitch blade units, the peak efficiency occurs at different outputs depending upon the blade. Now, let us talk about turbine control, use of governor and the mechanism employed to control the flow velocity in turbine. This is the speed control of turbine, in which the governor adjusts the flow of the water through the turbine to balance the input power with the load. In case of small plants, like we are talking about a micro hydel for capacity 100 kilowatt or less, load control is also used, where excess load is diverted to dummy load to maintain with constant speed. With an isolated system, the governor controls the frequency. In interconnected system, the governor may be used to regulate the unit load and may contribute to the system frequency control. Now, let us talk about considerations for selecting governor and control system. Governor and control system for small hydro units, especially in developing countries, have to be selected keeping in view the numerous factors. Number 1 or number A, you can say traditional mechanical flow control governor with mechanical hydraulic device is complex, demanding maintenance at very high cost. Then further performance requirements of stability and sensitivity like dead band, dead time and dashpot time, especially for intercooled units, may not be met by mechanical governors. Then electronic and digital flow governors can take up the plant control function. Nowadays, even completely automated system are used for governing the hydro plants. Then cost of speed control and automation with currently is installed analogy flow governors, unit control and protection system is high. This system requires attended operation and are mostly based on a large capacity of hydro units, this making most of the units very costly and uneconomical to operate. The manpower is available for a small hydro plant operation is unskilled, and further adequate supervision is not feasible. Load factors for standalone micro hydels are usually low, affecting the economic viability. Flow control turbine governors are expensive and not recommended for small hydro units in micro hydel range. Electronic load control governing system with water cooled hot water tanks, ballast load for unit size up to 100 kilowatt can be used. So, these are the various mechanism of governing a hydro turbine, or you can say hydel power plant. Now, we will talk about modern practice regarding governor and plant control. Control of a hydro plant generating units is typically performed from a central control board containing iron vane meters, hard wire, control switches and large number of auxiliary relays to perform the unit start stop operations. All the necessary sensors and controls required to operate the unit or units were hardwired to the control panels, allowing control of power stations and centralized control room. Modern digital integrated control and protection system includes programmable logic controls, that is called as PLCs, distributed computer control system or personal computer control system not only provide supervisory control and data acquisition, but also flexibility in control, alarming sequencing, remote communication in a cost effective fashion, and has been specifically recommended for SHPs in India under UNDP GEF project. Now, let us talk about modern typical digital shunt load governor for micro hydels. A typical digital shunt load governors was developed in India. These controllers are reported to be working successfully in India and abroad for the last 7 years. These generations controllers, also called as load shunt governors, are digitally controlled electronic governors for controlling micro hydel power plants up to 200 kilowatt capacity by controlling the output load only. Standard controllable loads like water heaters are provided along with the governor systems, and the load on the machine is maintained using these load in such a way so that the user gets stable voltage and frequency. No major input control is required, resulting in considerable saving in cost of equipment and civil works. Dummy loads can also be replaced by useful loads. Load controller can be designed to manage the useful load system for surplus energy. It is a foolproof and suitable especially for unintended operation in remote rural area of developing countries by unskilled operator. Now, let us know some advantages of shunt load generator. The generator, this type of generator always generates the maximum power possible. The generation is not immediately required, is used up in secondary loads that are controlled by triacs. The secondary loads can be useful for various purposes, and the overall system efficiency can be extremely high. Few other advantages also I have discussed. Since the control is by digital means with the speed as reference, the response of the governor to change the frequency can be faster and more accurate as compared to the mechanical governing or by electronic governing based on current voltages. There are some more advantages of shunt governors also that you will get in detail in my PPT, which I will share with you. Now, let us talk about induction generator. Induction generator are essentially same as induction motors. When rotated at super synchronous speeds, the machine works in generation mode, feeding kilowatt directly into the grid. The power output is determined by slip torque characteristics of the machine. The speed of the torque generator set does not need to be controlled by a governor, nor there is a need for a voltage regulator. However, the machine draws kVAR from the system for its excitation. Consequently, net power factor of the unit is very low. Further, the generation operation is fully dependent on a live grid. Hence, if supply from grid is interrupted by tripping anywhere, the generation from the unit will cease. It means it will stop. Also, the unit will tend to go to runaway speed, for which special protection will have to be particularly provided. Now, capacity and rating kilowatt in kilowatt. The kilowatt rating of the generator should be compatible with the kilowatt rating of the turbine. You cannot use different kilowatt turbine and different kilowatt generator. The most common turbine types that are used, we have already discussed: Francis, fixed blade propeller and adjustable blade propeller Kaplan. Each turbine types has different operating characteristics and impose a different set of generator design criteria to correctly match the generator to be connected to the turbine. For any turbine type, however, the generator should have the sufficient continuous capacity to handle maximum kilowatt available from the turbine at 100% gate without the generator exceeding its rated nameplate temperature rise. In determining generator capacity, any possible further changes to the project, such as raising the forebay level, increasing turbine output capabilities, should be considered. In a variable head power plant, the turbine output may vary depending upon available head. In general, the generator is rated for the turbine output at rated head. In peaking power plant, higher generator kilowatt rating could be specified to take care of possible higher turbine output. Economic analysis is required for this purpose at the cost, as the cost will increase. The generator capacity remains unutilized when heads are low. Now, let us talk about kVAR, that is kVA rating, and power factors. kVA and power factors is fixed by considerations of interconnected transmission system and location of the power plant with respect to load center. These requirements include a considerations of anticipated load, the electrical location of the plant relative to the power system load centers, the transmission lines, the substations and distribution facilities involved. When a generator is connected to the load through a transformer bank, the determination of the voltage is generally based on economic factor. Generator cost for unit for a fixed kVA rating and speed vary with the voltage, and these change in cost must be balanced against corresponding cost of generator leads, then instrument, transformers, surge protective equipments involved, etc., etc. The possibilities of load connected directly to the generator may influence the selection of the generator voltage. The generator frequency is determined by the frequency of the system to which it will be connected. Then some recommendations I have given for rated voltage generator of different output for economic reasons. Up to 750 we can go for 415 volt. In between 751 to 2000 kilowatt we go for 3.3 kilovolt. 2500 to 5000 kilowatt we go for 6.6 kilovolt, and then more than 5000 we go for 11 kilovolt. Now, let us talk about in brief speed and weight with respect to generator and turbine combination. The speed of a generator is established by the turbine speed. The turbine speed for maximum efficiency corresponding to an even number of generating poles should be determined by the hydraulic turbines. Generator dimensions and weights vary inversely with the speed, like shipping weights are generally 10 to 15% more than net weights. The weight of the assembled rotor on the shaft is generally a little less than one half of the total weight of the generator. The powerhouse cranes must have sufficient capacity to handle the assembled rotor on the shaft. Now let us talk about the categories of generator assembly. 4 categories of generator assembly which depends upon the megawatt rating and size of the generator we need to know here. We will briefly discuss one by one. So category 1, factory assembled generators that are shipped to the site completely assembled. Then we have category 1 point also I would like to add that category 1 generators are usually less than 5 megawatt, but the classification also depends on the RPM selected, unit speed, weight and the method of transportation to the site. Then category 2, it is factory assembled generators that are shipped to the field as 2 integral component parts, rotor and stator, or sometimes 3 component parts, rotor and 2 stator halves. Those are usually between 5 and 15 megawatt. Then we have category 3, generators that require field assembly of the stator but can have the rotor shift to the site as an integral component part. These category 3 generators are usually between 0 to 50 megawatt capacity. Category 4 generators, these require complete assembly of the stator and the rotor at the site itself. These are usually greater than 50 megawatt. Then we are going to see one discussion, very critical discussion, construction of large hydro generators. Types of generators, we have vertical shaft generators, the detailed explanation you will get in my PPT. Then we have umbrella type generators which are used for some you can say 200 RPM. Then we have semi umbrella type generators which are being used for medium speed, say 150 to 300 RPM. Then we have a combination of umbrella and semi umbrella design that are used for 165 megawatt capacity having a speed of 300 or more than 300 RPM. Conventional standard type of generator, this type of generator can be used up to 1000 RPM. Prior to introduction of umbrella and semi umbrella design, conventional design comprised of top mounted thrust and guide bearing supported on heavy brackets which are capable of supporting total weight of the generator. Now let us have a look at generator component. First one is the stator. The generator stator consists of stator foundation, it supports all members, a stator frame, stator core and a stator windings. The generator stator frame structural members provide support for the stator core and other machine. The generator stator frame or yoke is generally fabricated from rolled steel plate, consists of rigidly welded structure of ample stiffness to withstand without distortion the stresses imposed by short circuits or by braking operations. Now let us have a look at the rotor structure. The rotor hub is attached directly to the generator shaft. The purpose of the rotor hub is to mount and fasten the rotor spider. Rotor spider consists of several mechanical arms that radiate outwards from the rotor hub. In physically large generators, this rotor consists of individual steel sheets stacked and bolted together to provide a continuous outside rotor perimeter to which the rotor poles are fastened. Then we have shaft. This will be mounted, it is common to generator and the turbine unit. A brake ring is provided on the lower side of the rotor, the wearing surface of which is removable and renewable. Fans are circulating air through which the stator and stators are attached to the rotor. Then we have brakes. Hydro generators are provided with mechanical friction braking system. This helps stop the generator's rotation after the unit is tipped off line. Stopping the unit at this point avoids wear on the thrust bearing. Then we have different types of bearing. In bearing we have thrust bearing. Few discussions on thrust bearing also we will see here. Thrust bearing in the generator is the most important bearing element in the generator turbine assembly, as it carries not only the weight of rotating generator parts but also the weight of turbine shaft and turbine runner in addition to the turbine thrust on the runner. Then we have bearing temperature indicator diagram that you will get in the PPT which I will share. So after we have seen the complete generator unit in detail, we have seen the rotor unit, we have seen the stator unit, we have seen the braking unit, we have seen the bearings, we have seen thrust. Now we have coolers. Closed circuits air cooling water to air coolers are normally provided for all modern hydro generations rated greater than 5 MVA. The coolers are situated around outside the periphery of the stator core. generators equipped with water to air coolers can be designed with smaller physical dimensions, reducing the cost of the generator. The generator cooling water normally is supplied from the penstock via a pressure reducing station or pumped from a tail race. In either case, automatic self cleaning filters must be provided in the cooling water supply lines to avoid frequent fouling or plugging of the water to air coolers. Now, in this lecture, I will conclude by discussing excitation system. A DC current has to be supplied to the field winding of a synchronous machine. The field winding is on the rotor itself. A special arrangement is necessary to connect the DC source to the field. All hydro generators are separately excited from the DC source through slip rings or collector rings and brushes. Slip rings are metal rings completely encircling the shaft on the machine, but insulated from the shaft. A brush rides on each slip ring. The positive in DC voltage source is connected to the one brush and negative end is connected to another one. Excitation systems supply and regulate the amount of DC current required by the generator field windings and include all power regulating control and protective element. So, this is it in this unit. I hope you all have enjoyed this session. This was very informative and very content bringing lecture, which will give you the basic components of a hydropower plant. We will again meet in our next lecture with some more details about hydropower plant. Thank you for listening. Thank you.